In section 1.3, we're going to talk about reasoning and proof. Now, I'm not sure how long this video is going to take, but I suspect we might have to break it into two videos, so just be prepared for that. Let's look at our first example, just to get us started. We want to find the sum of the first 100 natural numbers, so 1 through 100. We want to find the total sum. Think about how we might do this. Now, that's a lot. If I had to grab a calculator, grab a paper and pencil and do 1 plus 2 plus 3 plus 4 plus 5 plus 6 and keep going. Number one, you don't even want to hear me keep going, do you? Number two, that would just take a really long time, right? I mean, it's possible. We can do it. How else could we do it? And how do we know it's true once we get the sum? So I want you to pause for a second and think about how you might find the sum of the numbers 1 through 100. And assuming you did that, let me show you a few different ideas. Now, you know how I like to make my husband a guinea pig, so I asked him to do this. And so what he did was he added these things up in groups. So he considered like the group 1 through 9 and 10 through 19, etc. And he thought, okay, well, if I add 10 or 1 through 9, let's just say 1 plus 2 plus 3, I can do that just by hand. And what do I get? If you add all those up, you get a total of 45. Now if I look at the next set, I see that by adding 10 plus 11 plus 12 all the way up to 19, what I'm really doing is adding 10 plus 1 plus 10 plus 2, etc., right? So I'm adding the numbers 1 through 9, and I'm also adding 10 how many times? 9 times, right? Oops, sorry, or rather 10 times, because I added in 10, 11, 12, all the way up through 19. So I've added 10 times. So in this group, I have 45, the numbers 1 through 9, plus 100. So he thought to himself, I'm going to have 45 how many times? I'm going to have it for the 1s group, the 10s group, 20s, all the way up through the 90s. So there's 10 groups of those. So 450 counts all the single digits. Then I'm going to have 10 times. I'm going to have 20 10 times. 30 10 times. And so forth. Up to 90 10 times. Plus 100, plus the number 100. And if you add all of those up, he actually gave himself a little shortcut. He said, well, if I know 1 through 9 adds to 45, then this must add to 4,500. So 4,600 plus another 450 gets me 50/50. And that is the sum. So I thought that was kind of a clever way to go about doing it, to group it, and he was convinced of his solution after that. Let me show you another way, which is really kind of crazy when you first think about it, and I don't think any of us, including myself, would think about this to start with. So I'm adding 1 through 100. I'm going to write it down twice, but the second time I'm going to write it down backwards. 98, and when I get all down to here, I get 1. And I'm going to add these all up. So if I add them up by columns, I get 101 each time. How many 101s do I have? Well, I have 100 of them. There were 100 spots. 100 of the 101s. But now I've counted my list twice. So I'm going to divide by 2. And I get 50/50. How cool is that? So it turns out if I add the numbers 1 up through n, whatever n is, I'm adding the integers, I can always say it's n times n plus 1 over 2. And that is always the sum. It's a really neat algebraic trick. So the title of this section is Reasoning and Proof. Now, what is proof? What is mathematical proof? Well, proof means different things to different people, and even in the math world, proof means different things. And it's not very well defined. In general, we could say it's justifying your responses. Proving your responses is justifying. And how far we expect people to go with their justification might be determined by who we're talking to and what we're writing for. So if I was trying to prove something to my 7-year-old daughter, I might not need but a little bit of evidence and she'll be convinced. But if I try to prove the same thing to my husband, he might need a lot more evidence or some real concrete logic to reach the same agreement with that fact. Here in this course, we mean general reasoning and justification when we say prove. And we're going to practice some logical notation and some if-then statements just to get you used to some of the terminology. And this might take us through the entire first part of the video. Inductive reasoning is one kind of justification or reasoning. This is the process of finding a conclusion by looking at examples and finding a pattern. So that's sort of what my husband did when he solved the sum problem, 1 through 100. He looked at smaller sections and used it to find the pattern to prove it. So inductive reasoning is examples leading to a pattern and using that. Deductive reasoning is finding a result or a conclusion based on assumptions in a step-by-step argument. So the process I outlined is more of a deductive argument. It didn't take smaller examples and lead up to the pattern. I just showed how logically I could find that in general. So this is logical step-by-step arguments. And it's definitely not based on examples. So you might not even talk about an example ever in deductive reasoning. By the way, it's very common for students to use inductive reasoning, and even my 205 students and my 206 students, I have to remind you guys all the time that one example does not equal a proof. So just because it works in one case doesn't mean it always works. For example, I could say, prove that all triangles have right angles. You say, well, of course that's not true. Well, here's a triangle with a right angle, and even if I draw it upside down, I could even have it kind of crooked. So here's 3 examples with right angles, therefore all triangles have right angles, right? Wrong. So a couple of examples does not necessarily lead to justification of a statement. All right, let's talk about a statement. Let's say I make the statement, if I go to the movies, then I eat popcorn. And this is true for me. I very rarely go to the movies. I think I went to a couple of the cheap kid shows last summer with my daughter. But if I'm going to spend the money to go to the movies, I'm darn well going to get that nice extra butter salt popcorn. So what is this statement saying? It's not saying anything about how often I eat popcorn or how often I go to the movies. It's not saying I can never eat popcorn at home. It's not even saying that I necessarily go to the movies. It's just saying that every time I go to the movies, I eat popcorn. This is an important idea in an if-then statement. So if-then. And so what we say is we're making this if P, then Q. So P and Q are statements. So this is P, I go to the movies, and Q is I eat popcorn. So some terminology. The converse of a statement is essentially the opposite of a statement. It says if Q, then P. So in terms of my movie theater popcorn, this would say, if I eat popcorn, then I go to the movies. Well, I didn't say that was necessarily true, right? I eat popcorn at home all the time. So this is not necessarily equivalent, and in fact, it's quite the opposite of the original statement. It is not logically equivalent. And in fact, it's not even logically really opposite. So just because I said the original statement doesn't mean I know anything about how often I eat popcorn otherwise. So this is not always the opposite, not always the same. The inverse is the negation of the statement. If not P, then not Q. This is not logically equivalent to the original either. Think about what this says. If I don't go to the movies, then I don't eat popcorn. Isn't that very similar to the converse? In fact, it's the exact same thing logically as the converse. This is saying I never eat popcorn outside the movie theater, and that's not true. The contrapositive, however, is logically equivalent to the original. It's if not Q, then not P. So let's think about what this says. If I don't eat popcorn, then and maybe I could say, I didn't or don't go to the movies. Maybe I could say if I didn't, then I didn't go to the movies. And this is where the English language gets a little bit tricky, is trying to figure out those kind of things like don't and didn't. But is this equivalent to the original? I said, if I go to the movies, I eat popcorn. Every time I go to the movies, I eat popcorn. So if I tell you I didn't eat popcorn yesterday, then you can conclude that I did not go to the movies yesterday. So this is logically equivalent to the original. So that means if I'm trying to prove a statement like if P then Q, I could prove the contrapositive instead, and sometimes that helps. Sometimes that's easier. So if we want to show an if-then statement to be true, we need to either show it using a deductive argument, so I assume that P is true and I show that Q is true, or maybe by an inductive argument, or I prove the contrapositive of the statement through a deductive argument. What if I want to show it's false? Well, then I only need to show one counterexample. So if you wanted to say, hey, you know what, Dr. V, I happen to know that what you just said is false because I saw you buying popcorn at the fair and eating it. Well, is that a counterexample? I'm eating popcorn outside of the movies. That's not a counterexample, is it? Okay, so instead Joe says, Dr. V, I've got it. I know that what you said is false because I saw you at the movies with your daughter and you got candy and no popcorn that day. That is a counterexample. So showing a counterexample is showing that P happens and not Q. That's a counterexample, and that shows that the statement P implies Q must be false. I must have been lying. So I went to the movies, but I didn't eat popcorn. That's a counterexample showing that my original statement was not true. Okay, we're going to stop here for the first video, and we're going to pick up the rest of examples 2 through 6 on the next part of the video.